In the following, we discuss the contribution of Industry 4.0 to sustainability in production. This includes two perspectives. First, energy flexibility, and second, process efficiency. We will start with energy flexibility. The question arises as to how the flexible and spontaneous use of energy can promote the sustainability of a company. But to do this, let's first address what flexibility means in the first place. Flexibility can be defined alongside 6 areas. First, engineering, how to best use the technical characteristics of the various assets to ensure that production or consumption levels can be continuously adjusted to changes in grid load. Energy systems, how the grid can be operated to prevent grid congestion and damaging blackouts. Entrepreneurial, how companies can be enabled to provide their flexibility to the systems in a profitable way. Economic, how current electricity markets or the design of new markets can be adapted so that flexibility can be traded efficiently. Regulatory, how the legal framework can be designed so that parties involved in flexibility trading can rely on binding legal rules and contracts. Last but not least, information systems research, how data can be collected, shared and used so that the necessary flexibility information is available and usable. Due to increasing fluctuations of renewable energies, the need for flexibility is also increasing. However, conventional plants which previously absorbed fluctuations and thus reduced volatility are to be shut down, which is why the lack of flexibility ultimately creates a gap in the system. To close the gap, new flexibility options are needed to ensure system stability and energy availability in future electricity systems. So demand and supply must be balanced to keep operating frequency constant. Deviation ultimately leads to instability, cascading outages, and potentially the collapse of a power system. So flexibility is the ability to cope with short and long-term changes and imbalances between electricity supply and demand. So a potential shutdown of conventional facilities leads to a loss of flexibility. This refers to the ability to control variability and uncertainty in the electricity system through a supply adjustments. In order to guarantee the desired continuous energy availability, concepts were developed to increase flexibility in the energy network. For that, we can look at the following flexibility options, which we will discuss in more detail afterwards. The respective sectors, read from top left to bottom right, refer to energy transmission, innovation and improvement of previously conventional energy generation, storage of energy such as power to X, the use of renewable energies and ultimately the regulation of demand. So let's start with transmission flexibility. The advantages are, for example, a better use of renewable production and low emissions during operation. The disadvantages include the transmission losses, especially at very long distances across national borders. In addition, landscape consumption and negative environmental impacts are, for example, emissions during construction, mining, feedstock processing, and operations such as thermal radiation leads through drought. Let's talk about conventional supply flexibility. So the advantages here are the use of renewable fuels such as eco-gas possible and use upgrade of existing facilities which avoids additional land consumption and construction of new infrastructure. The disadvantages refer to high carbon emissions from conventional plants and typically are not in line with the overall goal of decarbonizing the electricity sector. Last but not least, let's talk about flexibility through renewables. So the advantages here are that we have low emissions during operation and typically easy removal of plants at the end of life. The disadvantages refer to landscape consumption and negative environmental impacts. Let's talk about storage flexibility. Here the advantages are typically low land use and easy removal of facilities at the end of life. The disadvantages refer to storage losses and inefficiencies, negative environmental impacts such as pollution from processing raw materials, for example. Last but not least, we have demand flexibility. So the advantages here are the use of synergies with existing production infrastructure, low emissions during operation, and typically no acceptance problems among the population. The disadvantages refer to loss of production efficiency with increased carbon emissions and increased mechanical wear and maintenance due to flexible plant operation. Industrial demand flexibility in particular offers great potential for a successful energy transition. We are aware that industrial companies have consistently high electricity consumption. The challenge with demand flexibility here is that neither the power system itself nor the current regulatory framework are designed for power system transformation and use of demand flexibility. However, security of system operation would be enhanced by offsetting the volatility of power generation through demand flexibility. However, for economic reasons, companies currently still often decide against using their flexibility potentials, as the costs of providing flexibility, including loss grid fee reductions, significantly exceed the revenues generated on corresponding flexibility markets. However, digitalization offers potentials for improvement at this point. The use of decentralized flexibility is made possible by progressive digitalization, which enables intelligent, highly time-resolved and rapid control of many resources, even very small ones. This would increase efficiency, reduce costs, and ultimately increase the attractiveness of demand flexibility.